I give you a 5-minute warning.
So my job here is to hopefully keep us a little bit honest in terms of let's look in the nearby universe and try and work out whether we actually see some of these mechanisms we've talked about. So why nearby? Well, basically we can actually start to resolve these processes. We can start to see down to these scales where we see entrainment, stellar winds, things like this. So we can look at the Milky Way, nearby AGN like Cecinus 1068, nearby huge bubbles, Perseus, and the object I'm going to be talking about, M31. And we can really start to see each of these feedback processes. The proximity means that we can also get down really deep in terms of measuring the faint emission or the faint stellar light. We can start to see the actual interaction taking place, the winds, the stars, the faint companions, and also push down in stellar mass. And then the other thing is that in the nearby universe we can actually measure the gas reservoir. We can measure H1 nice and easily. We can measure CO nice and easily. We can even get other lines. We can get lines of sight through nearby galaxies with quasars. We can really get everything else associated with these. Now, like I said, the example I'm going to talk about is M31, which sort of doesn't fit in some respects. It's not a massive elliptical. It's sitting in a small group, but I'll suggest that we can start to see a process in which quenching occur and a process in which quiescence can be maintained. So, like I said, Andromeda, we get everything. We get the ultraviolet, optical, near-infrared nice and easily. We get these out to large scale lengths. We can go far out in these objects. We get the dust, huge dust maps. We get all the ionized gas in H alpha. We get the cold dust. We get the CO. We can see every single part of the disk of Andromeda. So let's take Andromeda as a galaxy. Let's add it all up and see what we end up with. This is the integrated SED of Andromeda, basically within the aperture I show here. There is dust emission, we can see some young blue stars, but in general it's actually quite old. And this was mentioned a little bit with the Much paper earlier this week, but here is our specific star formation versus stellar mass plot from Sloan. Andromeda falls about here. It's in this process of what we would call quenching, sort of like what Kevin called before. It's a disk, but we're falling off the star formation regime into the non-star forming regime. So is this a galaxy in which we're starting to see quenching in process? Now the mass, the stellar mass is about right. Okay, so it's about 5 by 10 to the 10 stellar masses. Determined again within that sort of aperture. Importantly, we can also go far out and resolve the dark matter halo as well from stellar rotation, planetary nebula and globular cluster rotation curves. So within, we can separate the rotation curve into bold, thick disk, thin disk, dark matter, and as further out, we can separate the stellar mass from dark matter and determine basically that within M200 we have 10 to 12 cell masses. And so, we're really right at this peak of transitioning from the build-up of mass to the lose-off of mass in Ben Moss's plot and the other plots we've seen in the abundance matching. So, this is a galaxy where we can actually say, is this a galaxy in the quenching process? Now, M31 does host a supermassive black hole, M31 star. There is no indication of any activity sort of within the last million years. In fact, from what I've read, that's even more quiescent than our own black hole.
I'm sorry, quenching,
I agree. It's
there's
right
no
at this
evidence
peak.
that there's a long-term change, right? And so I think of quenching as something that what happens, it's not like I'm taking this and just drinking a tiny little sip every once in a while and thinking, God, I feel quenched, right?
It feels
I drink the whole damn thing, and then I feel good. And this is what, and the idea of quenching was that it's relatively fast process. And I think in this case, and in most other spiral galaxy cases, there's no evidence of something quick happening.
Then this is the case then. So we are sitting in this place people call the Green Valley. Now, if this is not rapid, then either we need to be cycling up and down here between them. Now,
Why
if you
can't I
sat
sit
down-
there forever?
If you sat there
Some
forever,
galaxies
we
do.
would see a huge number of galaxies there. Why don't we
That's
see a
not
huge
obvious.
number of galaxies there?
So just to raise a point about that, the way in which we calculate the stellar mass for M31 is very different from the way in which sloan stellar masses were calculated, most likely.
In some respects, yes.
You can
Right?
often
So,
very easily move that point slightly to
no,
the-
factor of 2. Basically, that's it. Right? So, but that's the true uncertainty for most of these stellar masses. I mean, the Sloan masses, they fit the mass to light ratio within the fibre, calibrate it with the radial gradient colours, fit it within the Gaussian magnitude, and get these things, right?
And move it by
And-
factor 2, it's suddenly a sequence.
Well,
What?
yeah,
Well,
I wouldn't put this on the main sequence.
no, if I reduce the size by factor 2.
I mean, look, I can easily change this. And this is one thing that we can do with nearby galaxies, right? Is I can concentrate my aperture purely on where the star formation is occurring. Or I can concentrate where the star formation is not. And move myself up and down on this plot. Is this realistic? No. Right? Because there's the surroundings for this. But we can use this as an example. So all of these comments I totally agree with, right? So the question is, what does it mean to be here? Is it a rapid process? Am I just catching Andromeda in a movement up or down from here? Now, I do disagree that, like most galaxies can stay there for significant amounts of time because we just don't see many galaxies there in terms of their colours or anything else.
Let's talk about it later.
All right.
And what about the stellar mass, the fact that your model overpredicts in the NIR?
No, this case is simply because, and this is the sad point of Andromeda, it's too close. So the two-mass standard Andromeda picture cuts out before my aperture, and that's exactly what you're seeing here. It's just missing some of the mass there. Right.
So you mean it matches if you make it smaller?
If I do within a certain aperture, I get a different SED, but then I end up with a full SED of a certain fraction.
Jonathan Sick is doing some really nice CFHT large-scale imaging.
Yeah, no, so there is the, what is it, the local group survey, or is this another one?
No, it's Jonathan Sick's Monforto.
Okay. But yeah, so I'd love to do these. I've also got the SDSS and things like that, but yeah. Like I said, we can go far out in Andromeda and deep down. And so this is the Pan-Andromeda, what's it called again? Pan-Andromeda Archaeological Survey, PANDAS. And basically, they've measured the full stellar structure around Andromeda, picking out amazing numbers of tidal dwarfs. I think they're up to 32 now, but don't quote me on it. But they measure these tidal streams far out. We're talking 40, 50 kiloparsecs from Andromeda. Things that sort of connect with its nearby companion M33, one of their little dwarfs they found in these things. And so we have an idea of these streams in there. And so, yes. And so the question I can say is, again, we can argue whether this is quenching or the movement up and down, but we can see that something has happened to Andromeda. We see that the centre is very quiescent. We see a strong ring of dust and gas and star formation. Maybe this is a process which things move up and down on this star formation versus stellar mass plots. And in this case, it's most likely interaction. So this circle highlights M32, basically one of the more compact dwarfs known out there. This thing is amazingly compact, has no dust, it has some X-ray, I've been told, Akos is going to follow me, and so it's extremely, extremely dead. Okay? There's no star formation, no dust, no gas, that people have looked into it. The thing is, though, it's most likely this object's been interacting with M32, just in case you couldn't guess from its position. And this may be causing some of the quenching we see in this object. Why it's moved from sort of where most of the spirals laid down in terms of its star formation rate. It's interacted, is slammed through the disk of Andromeda and caused a ripple to push out most of the gas from the centre, leaving this tidal trail of stars, and may have even pushed out some of the gas. Now, there's a whole number of dwarfs around Andromeda, and several of them have likely interacted in the same way. And so you may have this regular process of objects going through and around Andromeda, affecting its gas, dragging out the tidal streams of stars we've seen, and maybe this is the process at which some galaxies move up and down in the star formation rate mass plot. The gas, as I said, we have a very good idea out, and this didn't come out so well. That's my fault for copying a paper. We can trace the H1 gas far out from Andromeda, so that the disk of Andromeda lies right within the circle. We can see H1 structures all the way out here, and a faint stream of H1 between M33 and Andromeda. Again, suggesting interactions have helped move some of the H1 away from the disk, maybe some of it's driven in, and affecting basically the fuel supply of Andromeda over these timescales. So, here's a process which galaxies can move up and down on time in terms of their star formation rates. What about quiescence? So this is sort of, pointing in the direction where Greg wanted to talk to me from the title, which is star formation. Like I said, M32, no star formation, but it's a companion. Let's move to Andromeda. Right at the centre, we have the bulge of Andromeda. Absolutely no star formations going on there. Okay, so this is an interesting thing and may give us insights again into how galaxies maintain their quiescence. Right at the centres. Outskirts, I don't know, but right at the centres, we may be getting ideas of what's going on here. So again, same process. Integrate this little aperture. This is now the SED of the bulge of Andromeda. It's dead. Right? It has an extremely red spectrum. All of this UV you see here is from evolved stars. There is dust emission, which you can see in the plot in the background. All of this is heated by old stars. In fact, it's so old in terms of its stars that most of this is actually being heated by red light, not blue light, not ultraviolet light. It's basically dominated by sort of GR light in terms of its heating curve.
What is the blue line?
The blue line sort of is an estimate for the unextincted stellar population. It's not perfect. In fact, I think it's still adding too many young stars, simply because of the model I was using to fit it, which is a code called MaxVis. And so I think this is even an overestimation of the number of young stars in there. But in any case, this model still says that star formation rate is non-existent. It's sort of the upper limit of which a stellar SED can distinguish the star formation rate. So 10 to the minus 11, 10 to the minus 12 specific star formation rates. And even then, you try and look at what the mean age of this, it's extremely old. You look at what stellar spectra gives for these objects, people have gone from 6 to 14 gigayears in terms of a single stellar population fit to the spectra of the bulge of Andromeda. And so, it's got no young stars. What it does have is dust and gas. So on the left here, you see a Herschel Pax 100 micron image of the centre, with this ring here being a 500 parsec radius thing. So we're talking central bulge here. Stuff you see right at the start here is actually from the disk in front of the bulge. On the left is H alpha. So there's definitely gas there. And if we presume the dust is associated with the more cool gas, then we get somewhere around 10 to the 6.5, 10 to the 7 solar masses of gas in there. Now this puts it at the lower limits of what Tim Davies sort of ellipticals are finding. In fact, I don't know if you could have even seen something here in terms of a mass to gas ratio in Tim's objects. There is CO in there, so there's been work where they Melchior et al. Basically put on apertures on several of these high point regions and have observed CO, and this CO has significant line widths. So we're talking 50 kilometers per second. So we're really, this CO is there, is moving in strange ways, and may even be multiple clouds, like you can see. So we have cold dust, we have cold gas, we have ionized gas within these objects. So we come to the point. We have gas in these objects, but we don't have star formation. So we need to keep the gas warm. Now, the ionized gas does follow the same structure as the dust. Right? We see the same sort of spiral structure. It's not exact, and from what we can see, it sort of lies on the outskirts of the dust emission. Spectra of these suggest, unsurprisingly, a liner-like emission with strong nitrogen 2 relative to H alpha. The line widths are large, but would suggest that if shocks are present, they're very low velocity. The interesting thing you can also see here is that compared to the stellar velocity dispersion of the bulge, the gas is rotating. So you can see between the southwest and northeast parts, basically along the major axis of Andromeda, a difference in the main velocity. So this gas is rotating, just right in the centre. Now, another reason why we say that there's no young stars in there is that there is Hubble imaging of the centre of Andromeda. So what I show here is the panchromatic Hubble Andromeda Treasury Survey by Julianne Del Canton, looking right at the centre. We can resolve out all of the most massive luminous stars in the bulge. Now, confusion means that it's very hard to push down, but the resolved stars are basically dominated by extreme horizontal branch stars, the things that Carl was talking about earlier today. So here's the centre moving in steps outwards. This is what Phil Rosenfeld got for this. So on the top you have the integrated Hubble UV light on these objects. This is the resolved stellar light. The post-AGB stars contribute significantly, but so do these extreme horizontal branch stars. Now, because the post-AGB stars are much more luminous, in terms of numbers, these extreme horizontal branch stars dominate. And in fact, they probably make up most of this light that we're unresolving within these objects. So we have a significant UV light, nowhere near what you'd get from star formation, but hard and maybe causing the ionization of the gas. What we also have is X-ray gas. So again, here's our infrared image of Andromeda. Center, we have this diffuse X-ray gas, which extends out past the plane. Right in the center, we have huge numbers of low mass X-ray binaries, along with some diffuse gas. Now, I've been told Akis would be talking about this in the next talk, but just know there is a significant amount of X-ray gas there. Most of this X-ray gas is probably heated by supernova 1s, but hopefully Akis will improve upon that. So we have X-rays, we have UV fields, we also have turbulent velocities, suggesting some interaction, whether it's with stars, whether it's gas is buoyant, or something keeping the CO line that's very large. What's dominating? I don't know, right? So we're following this up with Sophia imaging to try and work out what's the excitation of the neutral gas, to see whether X-rays are dominating, UV photons are dominating, or turbulence is dominating, and we'll hopefully get an idea. The optical is not giving us a clue because, as we've heard, Post-EGB stars will give us liner-like emission. X-rays will give us liner-like emission. Shocks will give us liner-like emission. So by itself, that doesn't resolve this issue. So, quenching in quiescence number 31. So nearby galaxies can give us the insights into these processes. Right? So the physics of these things have to be resolved. Nearby galaxies are a way to do it. M31 is in between these quiescent galaxies, these star-forming galaxies. Is it being quenched? Well, we've had a debate on this, but I do state that the M31 is a perfect testbed for not just quiescence, like I suggested, but also we can look at the star-forming ring, and we can get star formation feedback as well. So we can use these processes to sort of help us work out the processes of feedback in our simulations and in more distant galaxies. Thank you.
Questions?
So the gas surface density in this central 500 parsecs is actually not very high then, it's below 10 solar mass per square parsec.
Exactly.
So that's consistent with it
It's-
not being forming stars.
It's very consistent. I mean, the thing is you also have, even if it was a little bit higher, you have a whole number of heating mechanisms there. So we actually know that some fraction is cooling, otherwise we wouldn't see the CO gas. But even this is not forming stars. So if we were able to resolve it even further, we'd probably see some clumps, but it's not forming stars. So something is maintaining this threshold above which it can form stars.
Any other questions?
Has there been any attempt made to map the CO gas in the centre of this, the bulge there?
Not that I know of, right? So there is large-scale maps of Andromeda, but they didn't have the sensitivity to get down to the CO gas in the centre. So the only one I know of is basically pointings of the most high extinction regions.
It would be very nice to see if this could be explained by rotation in the large line that you see.
But, well, remember, this is a small pointing on one region on one side of it. So
You've
this...
got a highly inclined disk, that's not going to be...
Yeah, but we're also off the major axis with one of these points. So my guess is it's not purely rotation.
The CO, when it's been seen, is extremely cold, so it's subthermal, very cold.
Any more questions? So I have one last quick question. So you said it looked from your graph that the post-HUBs and these extreme horizontal branches are similar in number density. Was that what you
No,
were saying?
similar in luminosity, in the surface brightness.
Okay.
Right? In terms of number density, the extreme horizontal branch just overwhelmed because they're
Okay.
factors of 10 to 100 lower in luminosity.
Okay, and then their UV light is then the extreme horizontal branch dominates. That's
So in terms of the resolved population, they're equal. The question is what's providing that large fraction of unresolved UV light. And given that the number density of stars is increasing as we go down, so the extreme horizontal branch are providing a large fraction of this unresolved stellar light.
thank you. Thank you, Brent.